Get started. So we've been learning up to now about series where we have terms that are positive and we are forming a series by taking the partial sum and taking the limit. Okay, and we've learned the issue, or the crux of the issue is how quickly these terms go down to zero. Yeah? The key example is 1 over n. These terms don't go down to zero fast enough. If they go faster in the sense of 1 over n to the p, for some p bigger than 1, then it's okay. If they go slower, then it is not okay. Right? Now we're going to talk for the first time about a series where the terms are not positive, where they're going to be positive and negative. And we're going to talk about something called an alternating series, where the terms go between positive, negative, positive, negative, positive, negative. Okay? This is the topic of today. And this is a very different situation. So suppose we have bk all big and equal to 0. We consider a series of this form. The sum from k is equal to 1 to infinity of -1 to the k minus 1 bk, like this. So this k minus 1 is just so that the first term is positive. It's not an important thing. We could also have just -1 to the k and factor out a -1. So don't get hung up on this. It's not important at all. It just makes it a little bit neater to write because we like to think of the first step we take as one going forward. So this first term here in k equals 1, this is -1 to the 0, b1, so it's b1. The next term, b2, it's -1 to the 2 minus 1, so it's -1, so b2 is negative, b3 is positive, b4 is negative, b5 is positive, and you see how it goes. Yeah? This is an alternating series. Cool. All right, so many of the things we've been talking about don't work when we have sequences of positive terms. We can't compare the series to just the function recreates it and consider the area underneath the graph, because now our blocks are both positive and negative, right? So we could have the fact that it's less than something means nothing, because if we're going to represent what this thing looks like, then we have, say, the first block is this positive block, the next block is this negative block. Now we're thinking about signed area. Next one is this positive block, B3, and so on. Yeah, so showing that this is underneath some function which has total integral from 1 to infinity converging means nothing anymore, because the negative blocks could be huge, right? So we have to have another way to think about this, another way to get to convergence. And we have a theorem that does this for us, which is a very powerful theorem, and it's in some sense quite a natural, well, it's actually a very natural theorem, and I will explain it in pictures as always. Theorem, alt, series, convergence, theorem. So, suppose we have an alternating series. So alternating series will be abbreviated to alt series from this point on. And it's like this. So without saying it, I'm always going to have it of this form, where the bk are positive. So k equals 1 to infinity, -1 to the k, bk. Okay, maybe I will say it. Where bk are positive, and they satisfy the following condition, that bk plus 1 is less than or equal to bk for all k. This is the first condition. And the second condition is that the limit as k tends to infinity, bk is equal to 0, then the series converges. Okay, so why is this true? So the metaphor I offered you to think about a series is taking an infinite collection of steps. And so far we've just been taking steps forward, yeah? And thinking about what happens if we take this infinite collection of steps forwards. But now we're not just taking steps forwards, we're going forwards and back. So this is what it looks like. You are this person right here, starting here at 0, and you are taking a step forward. And your step size is b1. Yeah? So after one step size, you're right here. And then your next thing that you do is taking a step back. Yeah? So after arriving here, you're going to take a step back. And your step back will be size b2. Right? So the length of this step size is b2 right here. Yeah? And then from this point where you are after 2 steps, you're going to take a step forward. Step 3. And every time you take a step, its length is always less than the length before. Yeah? That's this condition. So here you are at B3. Yeah? And you keep doing this. Ever onwards. Okay? So imagine we keep doing this, we keep doing this, we keep doing this. What kind of picture are we going to see when we do something like this? It's going to be something like this, right? We're going to go forwards, backwards, forwards, backwards. And you can see we're getting trapped into this smaller and smaller region here, yeah? Because every time we take a next step, the length of the step we take is less than the length of the step we had before, right? Like this. Yeah? So imagine we are, say, this picture's getting very small. So imagine we're here, yeah? And let's take this next one here. Let's imagine we're right here. So we're here after the nth step. So this is where we are, the nth step. And let's blow up this picture and see what it looks like. So this is our magnifying glass, or microscope, whichever metaphor you want. And here we are at the nth step. We are here. Okay, so we've just taken the nth step. We are here. When we've taken the nth step, that means we are at the Sn partial sum, right? We've done n steps. We are here at the Sn partial sum. And we've just moved forward by this step, Bn. Yeah? Then the next thing we do is to move back by Bn plus 1. And then from here we go forward by Bn plus 2. Yeah? But notice, at Bn plus 2, we are not as far to the right as we were at the nth step, because Bn plus 1 is less than Bn, and Bn plus 2 is less than Bn plus 1, right? So after moving back like this, we are somewhere between here, and then we move forward by something which is less than this length. So we're still trapped between these two lines. Thank you for the question. Yeah. So once again, here we are on the nth step. We take the nth plus 1 step, we go backwards, we're trapped between these lines. We take the nth plus 2th step, we are still trapped between these lines. Yeah? And then we take the nth plus 3 step. Since it is less than the length of the nth plus 2th step, we are somewhere here, still trapped between these lines. Yeah? The nth plus 4, still trapped between these lines, nth plus 5. From wherever we are onwards, we are trapped between these lines right here. We are trapped between these lines right here. Yeah? You see what I mean? Yeah? So, if this is me, and I'm this guy taking my infinite collection of steps, I take whatever, some big step forward perhaps, then smaller step back, and a smaller step back, and a smaller step back. Yeah? And as I keep doing this over and over again, by definition of this condition, my step sizes are getting smaller and smaller and smaller, and I'm just moving forward and backward. So I'm going forward, backward, forward, backward, forward, backward, but with smaller and smaller, smaller, smaller step sizes. Yeah? And I'm trapped between a more and more narrow area. Yeah? Yeah? So after doing whatever, after doing, I don't know, after doing any big number you like, number of steps, then the area I'm trapped within is incredibly, incredibly small. Yeah? And that area still gets smaller and smaller and smaller. Yeah? And that is very much, in fact it is, converging to a limit. It means that if you keep watching me do this forever, then after a long time, my step size will be so small that I'm going forward and backward by such a tiny amount that you can barely see me move it. Yeah? And at infinity, it'll be the case that I've actually stopped moving. I've come to some particular position. Yeah? So what is the definition of a limit? It means that we have some sequence getting closer and closer and closer to some particular answer, yeah, as the terms go to infinity. And what does it mean for a series to converge? It means that the Sn partial sums tends closer and closer to some particular answer, right? And that's what's happening when you're watching me. So after watching me long enough, I've taken the Snth step, I'm on the Sn partial sum, and then the Sn plus 1 is so very close, and the Sn plus 2 is so very close that you can barely see me moving, and I seem stiller and stiller and stiller the longer you watch me, which is exactly converging to a limit. Yeah? Give me the thumbs up. So later we're going to have we're going to think about this in a more precise way, but that's good enough for us for the time being. This condition and this condition, I hope, convinces you with this picture that we do actually converge to a limit when we take this alternating sum. And the key point is that we don't care about how quickly these terms go down to zero. Previously, we had to think a lot about this. We had to take our series, we had to check that it converges to zero fast enough, either by the integral test or the comparison test. Yeah? Now we don't have that condition. Now we just have that these terms go down to zero at any rate at all. And that is one of the key things that you need to understand from this. And this is one of the key things that the examiner is going to try and test you on. Because at this point, many of you, or at least all of you, are aware of the necessity for a series of positive terms to go down to zero sufficiently fast. And many students who don't have a particularly clear understanding have extracted that if you sum 1 over n to the p for p bigger than 1, then you're okay. And they have this as one of the things that they feel confident with. And then you could be asked some question about an alternating series where it's something like this. And your memory will go, oh, they're trying to, I know this is a square root, this is less than 1, it's not going to converge, when actually it's not the case. It is going to converge because this thing will satisfy our conditions. These terms are going down to zero, and this isn't a problem. So many students will just get this wrong because they'll just look at this expression and go, 1 over square root of n, I know this, that's not going to converge. Yeah, but it's not 1 over square root of n, it's minus 1, minus 1 to the n square root of n. Say that again, it's minus 1 to the n over square root of n. So this is something that maybe 15 to 20% of students get at least one question wrong of this kind every time we test this. But it isn't a difficult thing. It isn't a difficult thing because you can see why this thing doesn't require us to go to zero at any particular rate. Yeah? So if you understand why this is the case, then you're not going to mix these things up. This is a kind of problem with memorization is that if you don't understand why, then something like this looks very similar to something like this. So symbolically, they look very similar expressions, but they mean completely different things. So if you don't have a picture of what these things mean, it's very easy to mix them up. If you just memorize the pattern of symbols as opposed to the meaning of what they represent, then this is easily mixed up with this. But the actual meaning of this is someone going forward, backward, forward, backward, forward, backward, forward, backward, forward, backward, forward, backward forever. And the meaning of this one is someone going forward, 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 forward forever. The meaning is completely different. They look very similar symbolically, but they mean completely different things. So if you are aware of this, if you have a meaning for these expressions, you're not going to make this mistake. You're not going to be one of the 20% who get trapped on some question like this. Okay? So get this fixed in your brain, if nothing else. There'll be, with high likelihood, a multiple choice question trying to trick you into thinking something like this doesn't converge because you're just used to looking at 1 over square root of n as not being converging. So if nothing else, just be aware that you don't have to care about how quickly this thing goes to 0. You just need it to go to 0 if it's alternating. All right, everybody with me? The sum from k equals 1 to infinity of minus 1 to the k of k squared over 3 plus 2k squared. Does this thing converge? What do you think? Okay. What about everybody else? What do you people think? So I hope this was what I had, right? So, oops, to the minus 1 to the k. Okay, good. So if we are looking at these terms, look at this, the limit as k tends to infinity of k squared 3 plus 2 k squared, right? This is the limit as k tends to infinity of k squared over 4k squared plus 12. K plus 9, and the important term is the k squared, so we can factor k squared top and bottom, and this just tends to 1 over 4, right? So if you're taking a step every second for 100 years, then k is an incredibly huge number, right? And it looks very much like you're taking a step of size quarter forward, quarter back, quarter forward, quarter back, and then for sure you're never going to converge to an answer. Yeah? You see what I mean? What about this? What about the sum from k equals 1 to infinity of minus 1 to the k over log of 2 plus k? So it does not converge, this one. What about this next guy? Do you think this thing converges? Okay. So your conclusion is that and indeed it does converge. So by alt series test, we just have that these terms, bk is 1 over log of 2 plus k, which is going to 0 very, very slowly, but it is going to 0. And we also know that as k increases, these terms steadily decrease. So bk plus 1 is indeed less than bk for all k. Right? Because log of 2k plus 1 is definitely bigger than log of 2 plus k. Yeah? because log is an increasing function. So it's definitely decreasing. And the limit as k tends to infinity of 1 over log of 2 plus k is equal to 0. It is rather easy to detect if something is converging if it's an alternating series. All we need is the terms to be decreasing and to go to 0. If we have an example like this, the sum k equals 1 to infinity of square root of n over n squared plus 3n plus 7 to the 1 over 4 minus 1 to the n. What about this? Does this converge? What do you think? Okay, let's do a survey. Thumbs up if you think it converges, thumbs down if you think it doesn't. All right, somebody tell me why it's not going to converge. Perfect. Again, the limit just doesn't tend to 0. Yeah? And we know by the we know by the divergence test that if the terms don't go down to 0, then there's no way it can converge, right? Aside from the fact that we see that this thing is just going to be like taking a step forward, step back, step forward, step back. In this case, the limit will be 1, right? We have this other theorem that if the terms don't go down to 0, then the thing can't possibly converge. And that makes sense to us as well, right? So this thing does not converge. This is easy. You can quickly rule these guys out, you know? If you have, no matter if it's alternating or anything else, if the terms don't go down to 0, it does not converge. Because the limit as n goes to infinity of square root of n over n squared plus 3n plus 7 to 1 over 4 is just equal to 1. Okay, let's do this one. What about this? This is example 3. What about this? The sum from n equals 1 to infinity of minus 1 to the n minus 1 of n squared over n to the 3 plus 1. Does it converge or not? Thumbs up if you think converge, thumbs down if you think not. So yeah, this is a lot like the harmonic series, but this alternating property it has means we don't care how quickly or how slowly it goes down to 0. Cool. All right. So this thing will converge because we think these terms go down to 0, but there's another condition we have to check. There's 2 conditions in the theorem. What's the second condition? Visualize it. Visualize it. So less than, good. Right. Our step sizes have to go down to 0. Start again. Our step sizes have to be decreasing, right? If they weren't decreasing, there's no way it could go down to 0. Yeah. So they have to go down to 0 and they have to be decreasing. And going down to 0 doesn't mean necessarily you're decreasing, right? You can have this collection of terms that does go down to 0, but every now and again it fails to be decreasing. Let me show you what I mean. So this is our sequence of terms Bn. It can certainly go down to 0, but every now and again there's a guy that just is like a little bit upwards. It's not necessarily, doesn't mean that it's decreasing the fact it's going down to 0. So we have to actually check this. This is part of the reason this is part of this reasoning. The fact that each step is smaller than the step before is why it gets trapped in this little thin strip here. Yeah? So we need to check that the terms are actually decreasing in order to apply the theorem. So solution. Let Bn be n squared over n to the 3 plus 1. Yeah? Need this to be decreasing. That Bn plus 1 is less than or equal to Bn in order to apply the theorem. Yeah? Because we know that the limit as n goes to infinity of Bn is equal to 0. Yeah? That for sure is true, yeah? Because the power on the top is 2 and the power on the bottom is 3. So that's the only thing we need to check. Huh? Cool. How are we going to check this? What's your advice about how we check this? What's your advice? How did we learn to check that something's decreasing? What methods do we have? Take the derivative of what? What function? Not rescues, but recovers. Rescues is a good word. Rescue. I'm happy with the word rescues because it's got the right image, but I use the word recovers. But okay, rescues is fine. So this is how we're going to visualize the sequence, right? So this would be B1, this would be B2, this would be B3, this would be B4, and so on. Yeah? And it's just a sequence, so we can't differentiate anything, right? There's no way to differentiate a sequence. We can't take the limit of f of x plus h minus f of x over h. There's no x involved in this. But we can find the function that recovers this sequence, right, which goes through all these points. In the language of maths, that's exactly asking for a function f such that f of n is equal to bn. Yeah? Because the graph of the function going through this point is exactly the same as that. That's what that thing means this. That at these integer points, 1, 2, 3, 4, the graph of the function equals bn. That's exactly what I'm drawing here. Yeah? So that's what we're looking for. So we need a function we need a function f such that this is true, and then we're going to take the derivative of the function and show it's decreasing. Because if it's decreasing, then for sure this sequence bn is decreasing. Yeah? So what is the function that recovers our sequence bn? All right. This is our series, right? This is the sum from n is equal to 1 to infinity of minus 1 to the n plus 1, n squared over n to the 3 plus 1. Yeah? And our function is what? Yeah? Because this thing does what we want. F of n is equal to n squared over n to the 3 plus 1 equals bn. So that's exactly the guy that we want. Yeah? Cool. Let's draw the picture again. We have terms 1, 2, 3, 4, 5, and so on. Yeah? And our function goes through these terms. So all we need to do is check that this thing is decreasing, and then we're all good. Yeah? All right, cool. So what are we going to do? We're just going to take the derivative. Huh? So f prime of x is equal to, it's the quotient rule, so put everything on the bottom squared, differentiate the top guy to x, leave the bottom guy alone, minus, leave the top guy alone, differentiate the bottom guy. Yeah, and then do the calculation. So we have 2x to the 4 here, but here we have minus 3x to the 4, so we have minus x to the 4, and then from this term we're going to have just plus 2x. And this is x to the 3 plus 1 squared. So long as x is bigger or equal to 2, this thing is definitely less than 0, right? So it's less than 0 for x bigger than or equal to 2. So that means from 2 onwards it's decreasing. Yeah? And that's good enough because we don't actually care about the first any finite number of terms. We don't care the convergence of the first. When we consider the convergence of a series, the first n number of terms is unimportant to us because it's just the sum of a finite collection of numbers, right? So when we look at this series here, the sum from n equals 1 to infinity minus 1 to the n plus 1, n squared over n to the 3 plus 1, then give me a big number, somebody. Give me your favorite big number. Okay, perfect. That's a good one. 1002. Yeah? And we have this plus the sum from n is equal to 1003 to infinity minus 1 n plus 1 n squared over n to the 3 plus 1. This thing right here is just a sum of a finite number of numbers, right? So no matter what terms we have, this thing is just adding up a finite number of numbers. This thing makes sense. This thing converges. Oh, converges is the wrong word. This thing just makes sense. There's nothing difficult. Nothing can possibly go wrong with this part. Yeah? So when we're talking about convergence of this expression, whether or not this expression makes sense, this part for sure makes sense, right? This for sure makes sense. Doesn't matter what the numbers are. If we add 1,002 numbers up, doesn't matter what they are. That thing makes sense, huh? That thing makes sense. So the thing that's required to make sense for this entire thing to make sense is this part right here. Huh? So we only have to care about the properties of our sequence that we're adding up in our series from some particular large number onwards, or small number, or any number. Yeah? And in this case, from 2 onwards, we know that the terms are decreasing. Yeah? So we are happy with this. This thing definitely converges. Yeah? This thing definitely converges. Yeah? So since bn plus 1 is less than bn for all n bigger than or equal to 2, then the sum from n equals 2 to infinity minus 1 to the n plus 1 n squared over n to the 3 plus 1 converges. Oh, I'm overrunning. And we are all good. Huh? Cool. I'm overrun already, but there's more stuff I have to explain. There's the real important thing about this is that we can estimate the difference between the partial sums and the actual sums. We can actually find how close the answer is to the full answer. And that is the alternating series error estimation test. So I'm going to present that next. If you have to leave now, as many of you have to, please watch the remainder of this video because that is something we're going to need. That is something we're going to need. Okay, for sure that will be tested. All right, so goodbye to all of you who have to leave. Now we're going to talk about the error estimation. So alt series error estimation. So as I talked about with respect to the integral test, we have the capacity to actually detect how close our partial sum is to the actual answer, which is incredibly useful because we can't write a program to actually compute this because nothing lasts forever, right? We can't loop a program infinitely many times, no matter how quickly it does a loop, to actually sum this expression and get an exact answer. Yeah? Yeah, life is finite, the world is finite. So if this is the thing that we really need to learn about, the best we can do is to get an approximate answer. We know that this thing does make sense. This is something that is a real, there is something which is this thing. This thing is a meaningful thing. It's a number. We don't know what it is. Yeah? We don't know what it is, but we can get close to it. We can get close to it. Because what is this thing? This thing is of this form. This is what an alternating series is. We have sum k equals 1 to infinity, minus 1 to the k minus 1, bk. Right? This is what we're going to call S, the actual answer. And the partial sum, Sn, is the sum from k equals 1 up to capital N of minus 1 to the k, b to the k. Yeah. And then we want to see how close this thing is to the actual answer. That's called the remainder. Rn is the actual answer minus the nth partial sum, and that's the same as summing from k equals capital N plus 1 to infinity minus 1 to the k. Oops, I should be consistent. Minus 1 to the bk. So we need to estimate this thing here. We need to estimate this thing here. That is the alt series estimation theorem. Start that again. The alt series estimation theorem allows us to estimate this thing here, and in a rather simple way. The answer is that the remainder is less than b capital N plus 1. That's the answer one. So maybe I should phrase this in a better way. say then. So this is the juice. This is the powerful thing, that we can understand how close the actual answer is to the nth partial sum by this estimate. If we take n steps, then the difference between the actual answer and our Sn partial sum is less than the nth plus 1 step. Now, you might think, okay, that looks complicated. Why the n plus 1 step? This is the theorem. So we have that Sn is the nth partial sum k equals 1 to capital N minus 1 to the k minus 1. Bk, S is the actual entire sum, k equals 1 to infinity, minus 1 to the k minus 1, bk, and n is the difference between the two, which is the sum from k equals capital N plus 1 to infinity, minus 1 to the k minus 1, bk. Okay, so we visualized this already. So we're going forward. Let me write the conclusion first of all. Then Rn is less than Bn plus 1. So we visualize this already. We go forward by B1. We go backwards by B2, right? And at some point we are somewhere, okay? So at the Snth partial sum, yeah, when we summed up the first n terms, right? Here we go, right? So that means this down here, say, is the nth step. This is Bn, and here we are. This is where we are physically standing when we've done n steps. So this is the Snth position. This is the position where we are at Sn. Yeah? So at Sn, right here. Yeah? But we keep going. So I'm going to change color to indicate that now we're doing these other guys. So now we're going backwards by Bn plus 1. Yeah? And then forwards by Bn plus 2. And then backwards by Bn plus 3. Yeah? And so on. And we saw this already, that we are trapped. We are trapped all the time. And if we're closely, we're actually trapped all the time between here and here, right? Because when we do the nth plus 1 step, we end up here. And we do the nth plus 2 step, we end up here, right? So here we are at Sn plus 2. Here we are at Sn plus 3, and so on. So let me do it this way. Imagine this is me doing my journey, okay? And then here I am. I arrive here at the nth step. So this is me at the nth step. Yeah? This is me. Then my next step is to step backwards by step size Bn plus 1. So I step backwards by step size Bn plus 1, and I'm here. And I'm here. Okay, so this length here is the Bnth plus 1 step size I'm stepping back. Yeah? Yeah? So I've stepped back. Now I'm here. Huh? Now I've done n plus 1 steps. Now I step forward by the n plus 2 step size. Yeah? But the n plus 2 step size is less than the nth plus 1 step size. So when I step forward, I'm not going beyond this board cleaner canister. Yeah? So when I step forward from here, I'm somewhere between the canister and the kitchen roll. Yeah? Give me a thumbs up. Okay. So here I am. Yeah? Here I am. I'm on the Bn plus 2 step. Now I'm going to step again the Bnth plus 3. But from the kitchen roll to me is Bn plus 2. Yeah? And Bn plus 3 is less than Bn plus 2. So when I step back, I'm not going to step back beyond the kitchen roll. I'm somewhere between where I am now, where this pen is, and the kitchen roll. Yeah? So I step back like this. Yeah? And I'm not beyond the kitchen roll. Yeah? Because again, this is the Bnth plus 3 step, which is less than the Bnth plus 2 step, which is between the kitchen roll and the red pen. Yeah? Are you with me? Give me feedback, people. Come on. And I step forward again, and I step forward again. I'm not going to get beyond this guy, yeah? Yeah? I'm not going to get beyond because I'm going to do the bnth plus 4 step, yeah? So I'm going to, again, be somewhere between the board cleaner and the kitchen roll. And I step back, again, between the board cleaner and the kitchen roll. Step forward, between the board cleaner and the kitchen roll. Step back, yeah? So I'm forever between these two things, the board cleaner and the kitchen roll, yeah? I'm never going to be anywhere except between these two things. And this is this, and this is this. These are my two blue lines. Yeah? So the answer, which is the limit of this process, wherever that thing is, wherever the answer is, it's somewhere between these two blue lines. Let's say it's here. Let's say this thing turns out to be where we are at infinity. This is the actual answer. This is S itself. S is between these two blue lines. But that means that S, this distance away from this thing here, which is Sn, is less than the length of this, or the width of this strip I've drawn here, is less than this length, which is Bn plus 1. Yeah? You see what I mean? Give me feedback, people. Give me feedback. Feedback of suddenly leaving is not encouraging. Before you leave, tell me if anything doesn't make sense. Okay, cool. And then that's exactly our theorem. That's exactly our theorem, right? Our theorem says that the difference between the Sn and the actual S is less than Bn plus 1, and that's exactly what we've seen here. Because we end up here at Sn, we go back by this step size, the next step size doesn't take us past this blue line, the next step size again doesn't take us as far, the next one doesn't take us as far. We're always trapped between these two blue lines forever, therefore this is true. This is true. Huh? So we see that this is true from this picture. This is true from this picture. And again, do this for yourself. Just watch this explanation and then take a blank sheet of paper and then try and recover the explanation of why the difference between the Sn partial sum and the S is less than Bn plus 1 from drawing a picture like this. Once you do this, once you convince yourself from drawing a picture like this, then you'll have this down, you'll believe in it, you'll be confident about it, and you'll be able to use it without fear. You'll be able to use it without fear because it makes sense to you. And this is powerful. Let's do an example. Let's use this thing. This is our next example, example 4. Find the sum from n equals 0 to infinity minus 1 to the n over n factorial correct to 3 decimal places. Yeah? Now, this is kind of a realistic thing you might want to have to do, right? Solution. All right, let's first think about what we mean by 3 decimal places, right? So if we consider 0.1, that's the same as 1 over 10, right? 0.01, that's the same as 1 over 100. And therefore 0.001 is 1 over 1,000. So correct within 3 decimal places is the same as saying the answer is within 1 over 1,000. Yeah? Yeah? Cool. So if we take the Sn partial sum, then that's the sum from n equals 0 to capital N, minus 1 to the n over n factorial. Yeah? And the actual answer itself is this thing here, right? And the difference between the two is Rn. So Rn is the difference between the two. The definition is up here, yeah? And that's the thing we want to estimate. And we know by this theorem that Rn, absolute value, is less than Bn plus 1, right? And in this example, Bn is 1 over n factorial, yeah? So the fact that we have -1 to the n as opposed to -1 to the n minus 1, again, is unimportant. We can just factor out a -1. So forget about whether it's n or n minus 1 or n plus 1. If it's alternating between plus or minus, that's all we care about. Yeah? Cool. So this is the thing. So let's write down in words what we need. So we need to have that b, capital N plus 1, is less than 1 over 1,000. Yeah? Because by the theorem, if b of capital N plus 1 is less than 1 over 1,000, then we are within 1 over 1,000 of the answer. So that's what we need. Yeah? That's what we need. All right. Since we have the expression of what Bn explicitly is, that's the same as saying 1 over capital N plus 1 factorial is less than 1 over 1,000. And that's the same as saying that 1,000 is less than n capital N plus 1 factorial. Yeah? Okay. Right. Let's see what happens when we consider numbers taken to some factorial. So, if we consider some of these terms. So, if we do, for example, 6 factorial. 6 factorial turns out to be 720. Yeah? Which is not good enough. That's not less than 1,000. But 7 factorial is 5,040. Yeah? So given that, how many terms do we require in order to get within the answer of 1 over 1,000? What will our capital N have to be in order for us to be within 1 over 1,000? So, by theorem, we have that for n is equal to 6, that 6 absolute value is less than 1 over 7 factorial, which is equal to 1 over 5,040. So that is the error that we require, right? So if we take the sum of the first terms up to n equals 6, what do we have? We have, starting from n is equal to 0, so the first term will just be 1. The next term will be minus 1 when n equals 1. The next term will be 1 over 2 factorial, which is 2. The next term will be minus 1 over 3 factorial, which is 6. The next term will be 1 over 4 factorial, which I don't know what it is, 24. Next term, minus 1 over 5 factorial, which is 120. And the final term is 1 over 6 factorial, which is 720. This thing is our answer. This is S6. This is our answer within 1 over 1,000, and this thing is actually 0.36805. So this is correct within 1 decimal place. So the actual answer is 0.36 something within 1 over 1,000 of this. Huh? Cool. Which is incredibly good precision, right? So this thing is not hard to, this is not trivial, but you can do this. You can add up these numbers here to form S6. Yeah? Yeah? So, pre-computer days, this is how we did this. We couldn't actually just plug this into a computer and get an answer. We had to do it by hand. But this is very good precision. This is very good precision. So we were able to build these things with incredibly fine tolerances, which were needed for many, many applications, to build very large buildings, to build steam engines, to build aircraft. We got very far in building society by using things like this that gave you an answer which was not the actual answer, but a very, very close answer because of the power of this kind of theorem. This is powerful. This is a powerful result. Okay, cool. Is everybody happy? Is this making sense? All right. This will be tested. The alternating series test is too easy just to test you on its convergence, or otherwise you might have a part of a multiple choice is trying to trick you into not remembering that the sequence of terms Bn don't have to go to 0 in any particular rate. But there will very likely be something like this, and it's even a good chance it'll be a free response because you have to do various things here. You have to think carefully. And the classic thing is to just get this wrong, is just to misremember this or just guess. But I claim you're not going to do this if you think about, if you understand why this theorem works. If we just keep adding up these terms, then we know the next term is minus 1 over 5,040, right? That's the step back we take. And then every other step we take is between where we were there and where we were before. And then we know for sure that the actual answer is less than 1 over 5,040 to the actual sixth partial sum. So the S6. So if you have a picture of why this is true, you're not going to get this wrong. If you add too many terms, then you'll still have an answer within that level of precision, but we won't get the marks because we don't want to do more work than required. So if you added or subtracted minus 1 over 5,040 to this and wrote that as the answer, yes, that is within that error, but it's not the least amount of work that you have to do, and that's what we're looking for. We're looking for you to find the least amount of work to get the answer within the precision required. So the correct answer is this. And if you keep adding terms, you won't get points. You will lose a lot of points when you get this right. All right, people. That's it for today. Have a great day. And I have office hour now, so stick around if you have any questions. All right.